Welcome to FMSP Online Revision. This session is for OCR D1 and the topic that we're going to be looking at is networks. So we'll start by having a look at the specification for networks, and then we'll work through a couple of questions to try and highlight as many points as possible and enable you to achieve the maximum number of marks possible. So let's just start. We've got 5 points here in the specification. So the first of them says we've got to be able to recall that a network is a graph in which each arc is assigned a weight, and we've got to be able to use networks as mathematical models. Then in part B, we've got to be able to apply Prim and Kruskal's algorithms in solving the minimum connector problems to find a minimum spanning tree. And notice that it's just in the case of Prim's algorithm that we need to be able to do that using a table or a matrix representation. Kruskal's algorithm we use from a network only. And then in part C, we've got to find a solution to the travelling salesperson problem in simple cases by determining an upper bound, which we do using the nearest neighbour method. Sometimes we're asked to try and improve the upper bound, so to look for shortcuts, but this is just, there isn't an algorithm for this, it is just a matter at looking at the route that we've taken using the nearest neighbour and seeing if we can improve it. So it is actually not necessary to use a specific algorithm here in part 2. And then in part 3 we've got to be able to determine a lower bound, which we do by deleting one vertex, one node from our network, and finding a minimum connector on the reduced network. And we'll have a look at that as we're going through some questions. And then in part D we've got to use Dijkstra's algorithm to determine the shortest path between two nodes, and then part E, solve simple cases of the route inspection problem for at most 6 nodes by consideration of all possible pairings. So like all questions in decision maths, it's really important that you show you're working carefully. And part E and using the route inspection problem is one where this is particularly important because students often leave out the details that are needed to get all the marks. So let's look first of all at a question. So some of the questions in D1 are quite long, so you do have to be aware of that. But let's have a look at this question and see if we can get the main points. So we've got a network, it represents a small village, the arcs represent the streets, and the weights on the arcs are the distances in kilometres. So just bearing that in mind, if you're given the units, then it's always a good idea to make sure you put those in your answer. Part 1. We've got to use Dijkstra's algorithm to find the shortest path from A to G, to show your working, including temporary labels, permanent labels, and the order in which permanent labels are assigned. And then we've got to write down the route of the shortest path. It then says that Hannah wants to deliver newsletters along every street, so we're asked about which standard network problem that she needs to use to find this shortest route that uses every arc. And then we're told that the total weight of all the arcs is 3.7 kilometres. Hannah knows that she will need to travel A, B and EF twice. So these are the ones here that quite clearly she will have to travel twice. So she knows that, and it then says, with this information, use an appropriate algorithm to find the length of the shortest route that Hannah can use. Show all your working. You may find that the lengths of the shortest paths between vertices by inspection, so we're not asked to do that using any particular method. But remember, we will have done Dijkstra, so we will have the shortest distance, so we can make use of part 1. So let's start by using Dijkstra's. So that's just the question, and just reminding you that what we've got to do is show all our working and write down the shortest path from A to G. So I have put on this slide the sort of boxes that you will need. So this is how we are going to show the temporary labels in this box here, and then we're going to show the permanent labels in this box on the right, and the order of labelling in the box on the left. So that is a fairly standard way of doing it. So we're trying to find the shortest path from A to G. So I'm going to start at A. That is going to be the first node, the first vertex that I've started with, and obviously the distance from A to A is 0, so we're going to start with that. Then remember what Dijkstra says. We now look at all the places we can go to from A. Now in this particular case there's only one we can go to, which is B. So the distance from O to B is 0.5, and as I say, that is the only place we can actually go to, so that immediately is going to be made permanent. So a permanent label of 0.5, and it's the second one that we're going to do. And now we need to be more careful, because of course from B we can go from B to D, so that will be 0.5 plus 0.1, which is 0.6. We could also go from B to C, which is 0.5 plus 0.2, which is 0.7. And what we have to do now is look at our temporary labels. So we have a temporary label of 0.6 here, and a temporary label of 0.7 there. And what we are told in Dijkstra's is that we take the smallest one, we make it permanent, and that is now the third node or third vertex that we have made permanent. So again, we now think about where we can go from D. So we could go from D to C, but of course that would be 0.6 plus 0.35. So if that was bigger, and it is bigger, than the temporary label we've already got, we do not replace the 0.7 by 0.95. So we just discount that one. We then consider that we could go from D to F, and that would be 0.6 plus 0.2, which is 0.8. And there's nowhere else we can go from D. So we now look at our temporary labels. We've got a 0.8 there and a 0.7 there. 0.7 is the smallest, so we'll put that in there, and it's the fourth node that we have made permanent. So we are now at C. So where can we go from C? Well, we can't go to D because that's already been made permanent. So the only thing we can do is to go from C to G. So 0.7 plus 1, which is 1.7. And that's as much as we can do. So we'll look at our temporary labels, 0.8 and 1.7. We take the smallest one. Now we're at F, so we think about where we can go. We could go to E, which would be 1.1. We could go from F to G this way, which would be 0.8 plus 0.45. Or we could go from F to G this way, which is 0.8 plus 0.6, but that is bigger, so we're not likely to do that. So 0.8 plus 0.45 is definitely smaller than 1.7 because it's 1.25. So we're going to replace that, and that now is our temporary label. So we look at our temporary labels, and we've got a 1.1 there, a 1.25 there, so this one now is becoming permanent and is going to be our sixth. And now all we have to do, since the only one now that has not been made permanent is this, which is 1.25, and that is the seventh one. So we now have the shortest distance of 1.25. So the shortest distance is 1.25, and that's kilometres. And we then have to work out the route. So it's often a good idea just to work backwards. So how did we get to G? Well, we came from F, because 0.8 plus 0.45 gave us the 1.25. So if we were at G, we came from F. How did we get from F? Well, to get from F, we must have come from D. 0.6 plus 0.2 gave us our 0.8. How did we get to D? Well, the way we got to D was to come from B. 0.5 plus 0.1, and we got to B from A. So our route is A, B, D, F, G. Now there were 5 marks for that question. You got 1 mark for your temporary labels, 1 mark for your permanent labels, 1 mark for the order of permanent labels, and then you also got a mark for showing this 1.7 as a temporary label, which you then subsequently replaced by 1.25, and then you got 1 mark for the route A, B, D, F, G. So you do need to be careful that you work through those in order. So let's have a look now what we need to do next. Hannah wants to deliver newsletters along every street. She will start and end at A. Which standard network problem does Hannah need to solve to find the shortest route that uses every arc? So hopefully you realise that it's the route inspection problem. And we get 1 mark for that. We're told that the total weight of all the arcs is 3.7. Hannah knows that she will need to travel A, B and EF twice, so she knows that she has to do these twice. So we don't really need to worry about those. With this information, use an appropriate algorithm to find the length of the shortest route that Hannah can use, and it says show all your working. So we'll need to do that very carefully. Now we know that we're going to have to repeat these, so we know that we're going to have to add this 0.5 and the 0.3, 0.8 on. But we don't now need to consider A and E as odd nodes, because we have to do that. So we're going to look at the order of the other nodes. So the odd nodes other than A and E are, so let's just check what they are. Well, B is not odd. Now that is even. D is definitely odd. C is odd. F is odd. And G is odd. So all the other nodes are odd. So we've sort of, just make sure you understand that we have we've left out this arc AB and the arc EF at the moment. So what we're going to do, we have 4 odd nodes, so we're going to pair them up. So DC would have length 0.3 and FG has length 0.45. Now remember, we want the shortest way of getting from F to G. So that will give us a total of 0.75. We could then pair off D and F, and then we would be left with C and G. Now DF will have length 0.65, that would be the shortest, that's a D. Just be careful when you find the length from C to G, you need to find the shortest one. So just check it's actually 0.95. So you're actually going to go along here. So you do need to be careful that you always find the shortest one. So that's a total distance of 1.6, so that doesn't look very good idea. So we'll just try the last pairing, which is DG and CF. So DG has length 0.65 and CF has length 0.5. So again, remember you're going this way to get from C to F. So it's 0.2 plus 0.1 plus 0.2, that sort of thing. So you're always looking for the shortest one. So that's a total distance of 1.15. So now we want to take the shortest one. So quite clearly this is going to be the shortest, isn't it? So these are the ones that we're going to do. So we want to find the length of the shortest route. So the length is going to be, so we have the 3.7, which we're told is the total length. We must remember that we're going to, Hannah knows that she was going to repeat AB, which is 0.5, and she was going to repeat EF, which is 0.3, but now she also has to repeat DC and FG, which is 0.75. And that will give us the shortest route. And if we add all those up, we get 5.25 kilometers. So again, just make sure that you make it absolutely clear that this is the one that we're choosing. So there were 5 marks for that particular bit. So you got 1 for each of these. So that was 3 of the marks. And then you got 1 for making sure that you had to add that on, and then an accuracy mark for adding on the 0.5 and 0.3 as well, and ending up with an answer of 5.25 kilometers. So that question has covered Dijkstra's and the route inspection problem. We're just going to have a look at another question now. Again, quite a lengthy question. We've got 5 rooms, A, B, C, D and E, connected to a computer network using expensive cabling. So the minute we see that it's expensive, we know we want to try and minimize the cost, keep it as short as possible. So Rob wants to find the cheapest way to connect the rooms by finding a minimum spanning tree for the cable lengths. Okay, so it says apply Prim's algorithm in a matrix or table form, starting at vertex A, showing all your working. We've got to write down the order in which the arcs were added to the tree, and draw the resulting tree and state the length of cable needed. So that's the first part, and then it says in the second part, a 6th room, F, is added to the computer network. The distances from F to each of the other rooms are given. And we've got to use our answer to part 1 to write down a lower bound for the length of the minimum tour that visits every vertex of the extended network, finishing where it starts. And then we've got to apply the nearest neighbour, starting at A, to find an upper bound. So we've got the travelling salesperson problem there, and we've got the minimum spanning tree problem using Prim. So let's have a look. So first of all, Prim's algorithm. So apply it starting at vertex A. So if we're starting at vertex A, then I'm going to circle A and cross out that row. So we're now looking down the column A, and we're looking for the shortest place that we can get to, which is B. So I'm going to circle that and put a little 1, and I'm going to write that down. So AB is the first arc, and it has length 12. We're now at B, so I'm going to circle B and cross out B. And the important thing to remember now is that you can look down both the column A and column B, and you're picking out the shortest one, the smallest number. So that will be this one. So that's the second one. So that's AD, and it will have length 15. So in terms of my tree, I've now got AB, which has length 12. I've got AD, which has length 15. So we have 5 nodes, so hopefully that you remember that means you need 4 arcs, so we need 2 more. So we now have got B cancelled out. Where did we get to? We got to D, so I'll circle D and cross out D. Now we can look down A, B and D, and we'll see that the shortest one now is definitely DE. So I'm going to bring that in next. So DE, I'll just put down here. Remember, it doesn't matter too much what your tree looks like. The important thing is that we're connecting up the right nodes. And that should be a 10. And now we are now at E, so I can circle that column, cross out E, but of course we know that we want to bring in C. So we want the shortest way of bringing in C, which will of course be this one. So that's my 4th arc. So that is DC, and it has length 20. So I'll just put that on there. So it said, apply Prim's algorithm, starting at A, showing all your working. Write down the order in which the arcs were added. So this was the order here. So that was the order in which we added them. Draw the resulting tree and state the length of the cable. So that's the last thing we've got to do. So the length of the cable, if we add those together, is 57 meters. So there were 4 marks for the question, 1 mark for completing the table correctly and getting another mark for getting the order correct. And then there was 1 mark for showing the information on a tree and 1 mark for giving the length, 57 meters. So if we have a look now at the next bit of the problem, oh no, here we have a slide. That's just to show you a slightly neater form of the tree and the order in which we have the arcs. We're now going to look, as I say, at the second part. So we've got the 6th room added. So what I've done here, and it's probably quite a good idea to do this, is I've just added on the extra column and the extra row to our table. So I would think, if I were doing this, and I would probably recommend that you do that. So it then says, use your answer to part 1 to write down a lower bound for the length of the minimum tour that visits every vertex of the extended network, finishing where it starts. Now, the lower bound, For the lower bound, we need a minimum spanning tree. So what we do for a lower bound is we delete a vertex. So let's just assume that the vertex, we didn't have F, so that, if you like, is our deleted vertex. So the lower bound is going to be found by the minimum spanning tree when F deleted, and then we need the two shortest arcs. From F, so the ones that will include F in our network. So that means it's going to be the 57, which we found as the minimum spanning tree, and we then want to just look up here or in our table here and see that the two shortest arcs are going to be 29 plus 30. So our lower bound is going to be all of that, which is 116 meters. So that was our lower bound. We then need to find an upper bound. Now the upper bound is found, as it says, by the nearest neighbour algorithm. So to get the nearest neighbour algorithm starting from A, so slightly different from prim and it's probably slightly easier, but we just need to be careful. So we're looking for the smallest place that we can go to, so that is definitely going to be the 12. So we're going to go from A to B, and we can cross off A now and we can cross these out. You can sometimes do this without, but we're now at B, so we'll cross out B. The difference here is that we now have got to go from B. So we cannot go from A now, so I've crossed that column out. So we have to go from B, so we're looking for the shortest one, which will be D. And the other thing that's quite useful to do is just to write the numbers in as you go along. So I'll put those in. So we're now at D. So I will cross B, we can't use anymore, and I'll cross out D. And now we want to see where we're going to go from D. Well, we could go to C, which is 20, or E, which is 10, or F, which is 35. Well, quite clearly we're going to go to E, because we're always looking for the shortest one. So we're now at E, and I'll cross out column D because we can't do that anymore. So we're now at E, so we can either go to C or F, and C is the shortest, so we'll go to C, which is a distance of 25. So where will we go? Well, we can go from to E, which is 20. Oh no, we've been to E and need to cross that out. So from C we'll have to go to F, which is a distance of 31. And the one thing that you must remember to do is that you must get back to where you started. So from F we have to go to A, and from F to A is 32. So the table it's not probably quite as important. I should just cross that out though. So we've got to everywhere now. We've completed the table, so this is going to give us an upper bound when we add all these numbers together, and all these added together, so we add these, should be 126 meters. So we have a lower bound of 116, an upper bound of 126, so the optimal route will be somewhere between those two. Now there were 4 marks for that question, that part of the question. There was 1 mark for seeing that you had to add the 2 shortest arcs to include F, which was the previously deleted vertex, so the 57, and then you had to add these 2, and 1 accuracy mark for getting 116. And then you got a mark for using the nearest neighbour correctly, and then an accuracy mark for getting 126. So I'm going to stop this session here and just remind you as always that the important thing to do is to work through as many questions as possible. Always the best way to revise.